So we're going to be looking at Chapter 5 now, which covers thermochemistry. Thermochemistry is the study of energy and its transformation in terms of chemical reactions. So for this first lesson, our objectives are to first and foremost be able to define, differentiate between the different types of energy. Going to be able to differentiate between temperature and heat. We're going to relate heat and work to energy, so show that relationship and use that for calculations. You're going to be able to explain the first law of thermodynamics, as well as define state functions and describe state functions. And you guys are going to understand enthalpy, or delta H, as we will refer to it for a lot of the lecture, and how it relates to thermochemical equations. So section 5.1 covers energy, or at least introduces us to energy. So energy refers to the ability to displace matter. So that ability to do work is what energy is actually pertaining to. And there's two major components, or two major groups of energy that you all may already be familiar with, and that's kinetic and potential energy. Kinetic energy is the energy of an object that's in motion, or an object that is moving. So moving objects are always going to be doing some sort of work. And the formula that you guys are going to be looking at is going to be E sub k, which refers to kinetic energy, is equal to half of your mass times your velocity squared. So this equation will sometimes come in handy depending on what you're given. There's plenty of practice problems in the book, and we may look at a few of them. Potential energy is the component of energy that is due to an object's position. So you have the possibility of actually performing work based on the position of an object or its chemical composition. And we'll talk about more of those details soon. So, as we know, energy is the capacity of something to do work. So there's different types of energy. A few that you should be familiar with, or may already be familiar with, are, for instance, radiant energy. That's energy that comes from the sun. It's the Earth's primary source of energy. It helps plants grow. It allows us to harness that energy, or we're able to harness that energy with cells, solar cells, things of that sort. Thermal energy is energy associated with the movement or motion of molecules and atoms. You guys see this when on a hot day, when you can see the air kind of wafting around, or when you see actual bubbles and stuff starting to form in your water when you boil it on the stove. Those are kind of examples of where you can actually visualize thermal energy. Chemical energy is something that we all interact with daily. We all eat breakfast, right? And we usually fill up our car once or twice a week. These are examples of stored energy, and these stored energy deposits are utilized to basically fuel our bodies and fuel our cars. So there's chemical energy. And nuclear energy is energy that's stored within a collection of neutrons and protons in the atom. So during radioactive decay or fusion or fission, basically we're going to be releasing energy as an element breaks down. Potential energy is energy that's available by virtue of an object's position. We know this. We've already discussed this in the previous slide. Electrostatic potential energy is a very important force that we're going to be looking into as the semester progresses. Electrostatic potential energy, or E sub EL, is a form of potential energy that arises from the attraction between charged particles. So you guys have already had an introduction to cations and anions, and you understand that positive and negative items attract one another. So in terms of the attraction between two ions, we're going to be utilizing this equation. We have a constant. The Q's represent the charges on the interacting objects, and those are all going to be divided by the distance between those two objects. Depending on what type of charge you have, so if you have like charges or opposite charges, that's going to dictate the potential energy that you actually see arising as they get closer or farther apart. So when you have like charges, like the example seen here, the greater the separation between the ions, okay, the lower the potential energy. And if we look down here at the oppositely charged ions, so the greater the separation between the opposite charges, the higher the potential energy. So if you just think about it mathematically, the bigger your denominator, the bigger your distance, the smaller your overall E sub L value is going to be. Now, when you're referring to like charges, right, whether it's negative and negative or positive and positive, you're always going to have a positive value. So the bigger that the larger that your distance is, the smaller your overall E sub L value is. When you're dealing with opposite charges, a negative and a positive, you're always going to get a negative sign. So you're always going to start in the negative potential energy value. The bigger the D value, the less negative you're going to become. And so you're going to get closer and closer to your zero value. So the higher your separation for those opposite charges, the higher your potential energy. The larger the separation for your like charges, the lower the E sub L value, or your electrostatic potential energy value. So why do we care about this chemically or on the atomic level? Okay, well, like charges, they don't necessarily want to be next to each other, so they're going to have higher energy if we force them to be in close proximity. So this state over here is more highly energetic than this state over here. And in the flip of that, okay, the opposite charges desperately want to be together. They want to attract each other. So basically they'd be in a really low state of energy, while separating them out gives them an opportunity to maybe interact with something else, or basically not be in its lowest energy state. So that makes sense energetically. It also makes sense mathematically. So this is the way we're going to look at electrostatic potential energy. So heat versus temperature. Well, first of all, let's go ahead and let's define them. So heat is the transfer of thermal energy, right? So that's one of the energies that we talked about. Basically, transfer of thermal energy between two objects or two bodies, as we have here, at different temperatures. Okay, so we always go from high heat to lower heat, right? That's the natural flow of thermal energy. Now, temperature, on the other hand, is the measure of the kinetic energy of the particles that are in whatever sample of matter we're looking at. Okay, and so that temperature that you measure on a thermometer is going to be directly proportional to your kinetic energy. Thermal energy and temperature are not the same thing. So temperature is actually measuring the transfer of the energy, the thermal energy, from your matter into your thermometer's liquid. Okay, as that liquid absorbs that energy, it expands. Okay, it separates out. That liquid starts to separate out. It rises. It gives you a thermometer. Gives the thermometer a new temperature value. Okay, so you're actually just measuring the energy of those particles. Thermal. So some of you may be just saying, okay, well, I don't really see a difference between temperature and thermal energy. Okay, well, we can look at it in this context. Okay, so everyone can agree that I can get a bathtub, fill it up with water, right? And I can get a cup of tea and fill it up with water. And I can make it where at some point in time they're going to have the exact same temperature value. I can stick a thermometer in the bathtub and read 40 degrees C. I can stick a thermometer in my coffee cup or my tea cup and measure the same temperature, right? Because the kinetic energy that's in, or that each of those particles has, is basically going to be equal. However, the thermal energy of the bathtub is not equal to the teacup. The reason why is because mass dictates, or the amount of substance dictates how much heat is going to be transferred. So by default, there's more thermal energy in the bathtub at 40 degrees C than there is in the teacup. And we can think about this in terms of transferring this liquid. So if I pour a teacup full of tea into a cold pool, right, there's not going to be very much effect, right? There's not going to be a huge temperature change. There's not going to be a lot of energy transferred to speed up the particles inside a cold pool. Now, if I do the exact same thing and dump the bathtub full of warm water into the pool, there's more thermal energy to be transferred, and subsequently I'm probably going to see a temperature increase in the cold pool. Alright, so temperature is just measuring basically the movement or the kinetic energy of the particles inside a body, and thermal energy is actually a construct that's determined by the amount of mass present, or the amount of substance present. Okay, so the way that we're going to be measuring units of energy, or the unit of energy that we're going to be using mostly in this class, is the joule. It's represented by a capital J. It's the SI unit of heat. Okay, but a lot of times the kilojoule is used instead. The reason why is because the joule can be fairly small when we're dealing with certain measurements or certain calculations. So to make it where there's a more easily recordable and more easily utilized number, we'll change them or convert them into the kilojoule. But you guys know how to convert between kilojoules and joules. You've done dimensional analysis on kilograms and grams. So you guys should be familiar with that. The calorie is actually a non-SI unit of energy, and it's actually related to the food calories that we look at. So 1 calorie, or the calorie that we see on a package, so capital C, as you can see here, as you can see here, that's actually equal to 1,000 cals, okay, or calories, little calories. All right. This interrelationship right here, 1 calorie is equal to 4.184 joules. This is actually something that's going to come up quite a bit. You're going to be expected to know this conversion factor. So make sure that you kind of put it in your memory, start working with it, because it will not be given to you most of the time. So the joule is our SI unit of energy. We'll be using that quite a bit over the next several sections. So thermochemistry, as we've established, is the study of the heat change in chemical reactions. So the first thing we probably need to do is actually define a few features of a reaction setup. So the first thing we need to look at is establishing what the system is. So the system is the part of the universe that we're actually focusing on. So whatever if it's the beaker, if it's a reaction flask, whatever it is that is being focused on, that is the system. Everything else that you're looking at is considered the surroundings. So basically the system is an arbitrarily defined item, and the surroundings is dictated by how you define the system. Okay, so there's different types of systems. There's open systems, closed systems, and isolated systems. And each of them have different features. So an open system is a system in which both mass and energy are able to be exchanged with the surroundings, excuse me. So in this case, as you can see, heat is being exchanged with the surroundings, and water vapor or mass is being exchanged with the surroundings. So the system is this bottle or this reaction flask, however you want to look at it. And in an open system, basically heat can flow wherever, water vapor can flow wherever. It's all good. Okay, so a closed system is one in which only energy, okay, is exchanged with the surroundings. So notice that there's a cork on top of this quote-unquote system. So basically nothing's leaving or entering the system except for heat, right? And heat energy is what we're familiar with now. So that's a closed system. An isolated system, so bomb calorimetry, things of that sort, things we'll kind of study in the next couple lectures, don't allow either energy or mass to be exchanged with the surroundings. So we have these 3 types of systems. You guys should be familiar with what they are able to exchange with the surroundings. Remember that your reaction flask in this case is the system. It's been defined that way. So therefore everything else surrounding is the quote-unquote surroundings. Okay, so there's two ways that we experience energy, at least in a tangible way, and that's by work and heat. Okay, so based on the equation that you see here, work is equal to force times distance. Okay, so when you move an object by applying a force over a distance, you've actually performed work. Okay, so you have your variables here. So when we lift something, like we pick up our little brother or sister, or our backpack and we put it on our backs, this is an example of performing work. We've taken an object, we've applied a force, and basically moved it a certain distance. Okay, heat energy, we experience that in the temperature changes in combustion engines, when we rub our hands together, when our hands are cold. Okay, these are all examples of energy changes or heat changes that we actually physically experience. So that being said, we are now familiar with the ways in which we actually experience energy, or at least typically experience energy. So now this brings us to section 5.2. We're going to look at the first law of thermodynamics. The first law of thermodynamics states that energy can be altered and changed, but it cannot be created or destroyed. So basically, you're either going to have energy that performs some sort of work, or it's going to produce heat. But basically, energy in the universe remains the same. Okay, so chemical energy lost by a reaction, okay, is equal to the energy gained by the surroundings. Okay, and we represent this by this relationship. So negative delta E. So delta E is going to represent, delta is going to represent change. So whenever you see this delta symbol, it means change in whatever variable. In this case, the variable is energy. Okay, and the subscript surroundings and system refer to surroundings and system. So internal energy is the sum of all the kinetic and potential energy of a specific system. However, this is really difficult to measure. We can't keep track of all of those variables, both variables at the same time. It would be very difficult to actually analyze, especially on the atomic and molecular levels. So really, normally what we focus on is actually delta E, which is change in energy. And delta E, guys, is going to be equal to the energy final minus the energy initial. So basically, what you're going to end up seeing is that your delta E value is going to have obviously a number value, right, because you're measuring the change. There's going to be units, right, and we talked about how we measure the units of energy, and a sign, okay, and that sign is going to dictate what's being gained or lost. So a positive delta E value means that energy has been gained from the surroundings. So the surroundings have supplied the heat for the reaction, or the temperature change, whatever change it is that you're seeing. Okay, a negative, delta E is going to mean that energy has been lost to the surroundings. Okay, so remember that we're looking at the equation delta E is equal to E final minus E initial. Okay, so this reaction on the left-hand side, we're starting with initial products, or initial energy that is higher than our final value. Okay, so in this case, the EF value is going to be smaller than the EI value, and when we subtract a larger number, okay, from a smaller number, you're going to end up with an overall negative value. Okay, so that's called an exothermic reaction. The energy doesn't just disappear. It actually gets given off as heat from the reaction to the surroundings. So that system, that reaction system, is actually going to provide energy to the surroundings. Okay, so that's an example of an exothermic reaction. I'll give you those definitions more specifically on the next slide. Okay, if we look at the reaction set up over here on the right-hand side, notice that the energy of my reactants starts out lower. okay, the energy of my products, okay, or my final item is actually larger. So in this case, when we subtract our energy initial from our energy final, right, that's going to give us an overall positive value, at least theoretically. So in this case, energy has not been released, right? There's no negative value. Okay, we're actually going to get a positive value for our delta E, and this is called an endo-thermic reaction, and that means that heat has been absorbed by the system. Okay, so exothermic processes are any process that gives off heat. So basically that transfer of thermal energy from the system to your surroundings. So any reaction that releases heat is going to be an exothermic reaction, and it's going to be characterized by that negative delta E value, right? Okay. Notice that in these equations here, okay, that we represent energy like it's a product, right? So we have our reactants on the left-hand side, we have our products, our prototypical products, but energy in an exothermic process is also a product. It's something that's given off. Okay, endothermic processes are processes in which heat actually is absorbed from the surroundings. So actually the system absorbs that heat from the surroundings. Okay, and so if you notice this, these reactions, these examples here, notice that your energy, okay, is on the left-hand side of the arrow. It's being utilized as a reactant. It's needed to make the reaction actually proceed. Okay, so endothermic processes, heat is absorbed into the system from the surroundings. Exothermic processes, heat is released from the reaction. Okay, and you should expect a positive delta E when you're dealing with endothermic processes. Okay, so let's go ahead and let's relate the first law of thermodynamics to our work and our heat. Okay, so we're going to be utilizing this equation here. Delta E, okay, or our change in energy, is going to be equal to Q plus W. So delta E is that internal energy change. Q represents heat, and W is work. Okay, so the heat is being observed as the exchange between the system and the surroundings, just like we discussed on the past couple of slides. Work is the work that's done to or by the system. So once again, everything is in reference to the system and the surroundings. So if the system does work, okay, actually perform some function or some movement, right, your W value is going to be negative. If work is done to the system, right, your W value is going to be positive. All right. In that same thought process, if heat is lost by the system, okay, your Q value, or your value representing heat, is going to be negative. If heat is gained, okay, if the system absorbs heat, your Q value is going to be positive. So we have a nice little handy-dandy chart over here that actually represents the expectations of what will happen. If heat is gained, so if your Q is positive and your work is done to the system, you know that you're going to get a net gain of energy. So your delta E is going to be positive. Okay, if you lose heat, okay, and you the work is done by the system, okay, you know that you're going to get an overall loss of energy. Okay, so your delta E will be negative. Okay, now it gets trickier when your Q and W values are values that could possibly give you negative or positive overall delta E. So calculations and stuff obviously have to be carried out. Okay, but you know that if you have completely positive or completely negative heat and work values, that you're going to get completely positive energy change values or completely negative energy change values respectively. So here's a little practice problem. It says that 555 joules of work is done on a gas sample to compress it into a cylinder, and 127 joules of heat escapes into the surroundings during the process. What is the change in internal energy? Okay, so in this case we have a Q value and a W value that's actually been given to us. Okay, so 555 joules of work is done on the gas sample. Okay, so in this case, because work is done onto the sample or onto the system, I know I have a positive work value. Okay, now it tells me that 127 joules of heat escapes into the surroundings. So what that means is that my heat has left the system. Okay, so for my surroundings, my system has given off heat to my surroundings. So I know in this case that I'm going to have a negative Q value. Okay, so when I go ahead and I plug these numbers, okay, into the equation, okay, do my basic math, negative 127 joules plus 555 joules, that's going to give me an overall positive delta E value. You always want to be careful with these types of calculations. You need to always make sure that the units, so joules and joules, match up, okay, or kilojoules and kilojoules match up. You never want to be adding two different units, okay, so that's why units matter. You want to make sure that you're always dealing with the same value of units, okay, so you don't add kilograms to grams. In that same way, you don't add kilojoules to joules. You have to make the units match. So our overall value here is positive. Okay, so we have a positive 428 joule energy change. Okay, so your overall reaction here, or your overall setup, is going to be an endothermic process. How do I know that? Well, my delta E is positive. So if my delta E is positive, I know that I have an endothermic reaction. So let's go ahead and let's look at the idea or the concept of a state function. Okay, so state functions are basically properties that are established by the state of the system, regardless of how that current condition was achieved. So some examples of state functions are energy, pressure, volume, temperature. Okay, so it doesn't matter the route that you take to get to your final values. All that matters is that you got there. So if we look at this example here, these two hikers, okay, the guy in the blue who took the blue path, okay, he took a pretty straightforward route, okay, while the hiker with the red route, he took kind of a more circuitous route to get to the top of the mountain. However, both of their changes of energy are going to be the same. Their potential energy is the same. Why? Because they're both in the same location. It doesn't matter that the red hiker took a whole lot longer and the trip took probably a lot more energy overall. All that matters is your final, state. Okay, so delta E, the value that we've been discussing, is a state function. Pressure change is a state function. Volume change, temperature change, always are going to be state functions. So the only thing you care about is your initial and final states in this situation. Something to note, however, is that Q and W are not state functions. Okay, so we just looked at delta E in terms of Q and W. So obviously we're going to be utilizing that to use more measurable or straightforward processes. But we're also going to take advantage of the fact that delta E doesn't care about how you started or what route you took, just what you ended up with. So we're going to take things that are very easily measurable and be able to compare them to something that could be very difficult to measure if we didn't consider, if we had to consider all of the details and all the little nitty-gritty routes that could have been taken.